This video is going to go through 3 worksheets: displacement time graphs, reading displacement time graphs, drawing displacement time graphs, and then reading velocity time graphs. So the first one we're going to do is reading displacement time graphs. So I've got a success criteria there, which we're going to work through for each question. And we'll start with the I do example. So the first thing we've got to do is work out the value of each square for time and for displacement. So these ones are all going to be easy. It's basically saying what's it going up in, and these are all going up in ones. Each square is worth 1 second or 1 metre. And then we're going to describe our graph. So from A to B, this bit here, we've got a straight line at an incline. So that's a constant velocity. And we can have a look. It's going for 2 seconds and it reaches 3 metres. From B to C, we now have a flat line and it stays at 3 metre displacement. So that means our object has to have stopped. It's stopped at the 3 metre mark, and we can have a look. It's stayed there from 2 seconds to 4 seconds. So if we do 4 take away 2, it stopped there for 2 seconds. And from C to D, we've got our line going down. This does not mean it's decelerating. It's still going to be at a constant velocity because it's a straight line, even though it's at an incline. Constant velocity, can't quite squeeze it in there. Constant velocity, but the reason it's going down is because it's going back to where it started. The item is travelling backwards. So it's gone for how many seconds? So from 4, 1, 2, 3, 4, 5. So it's gone for 5 seconds to reach 0 metres. That's where it ends up. Then we've got to calculate our velocities. So from A to B. So we're going to use our formula triangle that I've got there. So we're going to do our displacement divided by our time. So from A to B, it goes to 3 metres, in 2 seconds. 3 divided by 2 is going to equal 1.5 metres per second minus 1. C to D, we're going to do the same thing. So it ends up travelling 3 metres in 5 seconds, which is going to give us 0.6 metres per second minus 1. If I asked for like the overall velocity of this graph, you would say 0 because it started and ended at the same point. So the total displacement is going to equal 0. Therefore, its overall velocity is going to equal 0. But we can work out the velocity of each part. The fastest part of the journey is going to be our largest velocity. So it's going to be from A to B. It's also the part on the graph that has got the steepest slope or the steepest incline. Okay, moving on to our next graph. A bit less of this one has been filled in. Same thing, we're going to start with what's each square and what's for time and displacement, and it goes up in ones again. A to B is a constant velocity, and it's going to be for 3 seconds. So I'm just looking at where this B is, and I'm marking on our graph 3 seconds until it reaches 1 metre. My next segment, B to C, again, it's a straight line, so it's going to be stopped. And it's going to be stopped at that 1 metre, it's not moved, and it's going to stay there for 2 seconds. And then finally we've got C to D, so we've got a curve. A curve can be accelerating or decelerating. The way to work out how, or which one it is to draw a few tangents to the graph. So that means a straight line, which is right where the curve is, and I'll show you one. So if I draw a tangent at what looks like kind of the steepest bit, I draw a straight line there. That's really steep, so it starts off going at a really high velocity. Then if I have a look over here when it's going a little bit of a lower velocity, we get a lower slope. So that starts at a high velocity and ends up at a low velocity. So it's got to be decelerating. And it's decelerating for 1, 2, 3, 4 seconds, and it stops at 5 for our displacement. Then we've got to have a look at our velocity from A to B. So what we're looking at is the change in displacement over the time. So we've got 1 divided by 3, which is going to be 0.3 recurring metres per second. And then from C to D, it's going to go through 1, 2, 3, 4. So it's going to change 4 metres. And then we're going to divide that by how long it takes, which is also 4 seconds. So it's going to be 1 metre per second. I will point out there that it should actually say average velocity from C to D. So because it's decelerating, that is an overall using the total displacement, total distance and total time that it's travelled. It will change. We'll have a slightly higher velocity at the beginning and a lower velocity at the end, but it averages out at 1 metre per second. And then the fastest part of our journey, so it's going to be at some point during our deceleration, and it's going to be the first bit here. So it's going to be, I'm going to write the beginning of deceleration, which is about, let's say, 5.1 seconds. So it's going to be just after 5 seconds when it starts to decelerate from a very high velocity. On to the back of our worksheet. So we've got 2 more examples to go through. So A to B, we have a curve there. This time, this is going to be accelerating because it starts at a very low velocity and ends up at quite a high one, so a steeper slope. So that's going to be accelerating. And it's going to be accelerating for 5 seconds and it ends up reaching 4 meters. B to C is a flat line. It's stopped at 4 meters where it reached and it stays there from 5 till 7. So that's 2 seconds. And then C to D, we've got a really tiny straight line here, a straight incline. So that's going to be a constant velocity. And it's going to be for 1 second and then it reaches 5 meters at the end. So we've got our velocity from A to B. Again, this is a curve. It should really say average velocity there from A to B. So we'll work out the total displacement was 4 and we're going to divide it by how long it took. 4 divided by 5. It's going to be 0.8 meters per second. And then from C to D, it's gone 1 meter and 1 second. So it's going to be 1 meter per second. So the fastest part of our journey is going to be from C to D. And moving on to our final example. And we've got a little challenge question at the bottom. So again, it goes up in ones. Most of your examples will be harder and go up in things other than ones. A to B, we've got a constant velocity for 3 seconds to reach 4 meters. B to C, it's stopped at 4 meters for 3 seconds. And C to D, it's again a constant velocity. What's different here is it's going in the opposite direction, but it's still a constant velocity. It's not decelerating just because it's going down. It's going to be for 3 seconds to end up at 0 meters. So from A to B, we can work out our velocity. Our displacement is 4. We're going to divide it by the 3 seconds that it took. So it's 1.3 recurring meters per second. And velocity from C to D, so this time it's gone 4 meters in 1, 2, 3 seconds, exactly the same, 1.3 meters per second. So the fastest part of the journey, A to B or C to D. It's not going to be from B to C because it's stopped there. And your challenge question, why have I never asked the velocity from B to C? And that is because in all of these graphs, or at least in the majority of them if I've done it correctly, it is because our item is stopped. There is no velocity. The velocity would just be 0. So would the overall velocity for the majority of these graphs because most of them end at the same point that it started. Moving on to our second worksheet, we're going to talk about drawing displacement time graphs. So we'll go through them one by one. First of all, a student walks from the shop to their home. They walk 40 seconds to reach 20 meters. They shop for 30 seconds and then they return home and it takes them 20 seconds. So we're first going to work out the total displacement. How far did they end up going away from their house? So they walked 20 meters, they stayed there and then they walked back. So the total displacement is going to be 20 meters. The total time, we're going to add up all the times. 40 plus 30 plus 20, 90 seconds. Once we've done that, we need to choose a sensible scale to go up in. So going up along the time axes, the x-axis, we can go up in tens. Just remember you are labelling the lines and not the spaces. And displacement, the best thing to go up in here is 5s. We do end up with a spare 25 meters that we're not going to use. but it's still the most sensible thing to go up in. So the first thing they're going to do is walk for 40 seconds to reach 20 metres. So we do a little square there. They stay there for 30 seconds, so we count little squares. I'm counting 1, 2, 3, and that is where I'm going to do my next square. And then they walk home in 20 seconds, so I count across 2 squares, 1, 2, 20 seconds, and they're going to end up exactly where they started. Your final step, using a ruler and pencil, never use a pen, always use a ruler, is to join up everything with a nice straight line, nice and accurately. And if you've used pencil, if you make a mistake, you can always go back and rub it out later. Only thing I've forgotten on this graph is to put my 0 point in. So that's the first graph. On to the second graph. We've got a fox running at a steady speed for 10 seconds to reach 15 metres. 10 seconds, 15 metres. It stops for 20 seconds. It runs another 10 metres away from its starting position. So for our displacement this time, we've got the first 15 metres. It then stops, doesn't go any further. Then it goes another 10. So our total displacement is going to be 25. And to work out our total time it's going to take, it first runs for 10 seconds, then 20 seconds, and then finally a 15 seconds. So it's going to be 45 seconds that the fox is running for. So we can plot our axes. So this time for along the time axes, we could go up in 10s, but that would mean that our graph would only be in half of our graph paper, and we can stretch this one out further. If we go up in 5s, we're going to end up going all the way up to 45, which means that our graph will take up the entirety of our graph paper, which is what we're aiming for. And then we can keep the axes up the side exactly the same because we're going to 25 metres. Now let's plot our points. It runs for 10 seconds to get to 15 metres. It then stops for 20 seconds, which takes us to 30 seconds. So because we've changed the scale for our time compared to our last question, you will need to check 20 seconds is going to be 4 boxes this time, not 2 boxes, because each box represents 5 seconds rather than 10. And then finally, 15 seconds goes 10 metres away. So most of our questions have gone back to our starting point at this stage, but this one doesn't. So it's going to go another 10 metres away. Once we've done all of those points, we join them together with our ruler. So we've got the first bit, so he's going at a constant velocity. Then he's stationary. And then finally, we have another constant velocity. He's a little bit slower than he was earlier. On to our final question. We've got a girl runs at a steady speed for 3 seconds to reach 4 metres. She stops for 3 seconds, and then she runs at a steady speed for a further 3 seconds to reach a final distance of 10 metres. So this one's worded a little bit differently, but it says she's reaching a final distance, or technically it should be a final displacement, of 10 metres. And the total time, 3, is taken her 9 seconds. So our scales are really easy for this one. We can go up in 1s along the bottom, labelling the lines, not the spaces. And up the side, we can spread it out. We could go up in 2s. I think that's the best way to make this fill half of the graph paper, or over half the graph paper. We're aiming for the whole thing. So first of all, she runs at a steady speed for 3 seconds to reach 4 metres. So 3 and 4 will do our first point. She stops for 3 seconds at exactly the same displacement because she's not gone any further. And then she runs a further 3 seconds to reach the final distance. It doesn't actually tell you how far she runs, just that she ends up at 10. You can work out from the graph that she's actually running 6 metres in that time. So this graph, once we've drawn our lines, looks like that. Onto our final worksheet, reading velocity time graphs. So it's very similar to the first worksheet we did on displacement time graphs, but we're talking about a velocity time graph instead. So our inclines, our gradients mean slightly different things. So we're going to start going through our success criteria as before, but it's slightly different success criteria. First of all, we work out what does our graph go up in, what's the scale for time and velocity. Same as before, this one is just going to be in 1s. And from A to B this time, along the straight line, because it's a velocity time graph rather than a displacement time graph, when we have a straight line like that, it means our velocity is changing over a certain amount of time, so it's a constant acceleration. This one is going to be for 2 seconds until it reaches 3 metres per second. So we tend to write in A level metres per second minus 1, but this was originally a sheet for Key Stage 3, so that's why it's like this. From B to C, if it was a displacement time graph, we'd say it stopped, but it hasn't, it's stayed at 3 meters per second. So that means it's a constant velocity at 3 meters per second, and it stays there for 2 seconds. And then from C to D is going back down, so that means it's decelerating, and it's decelerating for 1, 2, 3, 4, 5 seconds, and it ends up going back to 0 again. So our acceleration from A to B, that's going to be our change in velocity divided by our time. So from A to B is 3 divided by 2, 1.5 meters per second squared, because it's acceleration. And our deceleration from C to D, so it's going to go 5 meters per second in 1, 2, 3, 4. Sorry, I meant that it's going to go 3. It's going from 3 to 0, so it's going to go 3 in 5 seconds. So that's going to be 0.6 meters per second squared. The final thing that this question is asking is the distance travelled by this graph. So what we need to work out is the area under this graph. So I really should have specified in the question, we'll just do the distance travelled from B to C, because that's where it's at a constant velocity. So that's the easiest bit to work out the area. So we're going to look at the area under the graph from B to C. I'll shade it in now. And we're going to do the height times the width. So it's going to be 2 wide, 3 high. So from B to C, it's travelled a total of 6 meters. On to our next graph. So again, this one just goes up in ones for both velocity and time. A to B, it's a nice straight line. So that's constant acceleration here, not constant velocity. It's because it's a velocity time graph. And it does that for 3 seconds until it reaches, just having a look at B here, until it reaches 1 meter per second. B to C is a flat line, so that is going to be a constant velocity. And it's going to stay at 1 meter per second for 2 seconds. And then C to D, so we've got a curved line. So you don't need to worry too much about which way it's curved with a velocity time graph. It just means that the acceleration is changing. And it's going to be changing for 1, 2, 3, 4 seconds. And that ends up going at 5 meters per second. So our acceleration from A to B is going to be worked out by doing our change in velocity divided by our time. So our change in velocity is 1 divided by 3. So it's going to be 0.3 recurring meters per second squared. And that's the only bit I've asked you to work out the acceleration of on this graph, because from B to Z it's not accelerating and C to D is a changing acceleration, and we don't really want to work out the area under a curve. So our distance travelled from B to C, first of all, that's this bit here. So it's gone across 2 and up 1. 2 times 1 is 2. A to B, I'll do it in different colours so you can see it. That's going to be a triangle, area under a triangle. So we do the same. We do the base times the height, so it's 3 times 1, but because it's a triangle, we then half it. So 3 times 1 is 3, half of that, 1.5. So between A and C, we now know it travels 1.5 and 2, 3.5, before it gets to the curve. And on the back of our worksheet, we've got 2 more graphs. So again, this one's just going to go up in ones. We've got a changing acceleration on that curve. Changing acceleration for, let's have a look, 5 seconds to reach 4 meters per second. B to C is going to be a constant velocity, and it stops at 4 and it stays there for 2 seconds. And C to D is a really tiny bit of graph there. It's a nice straight line, so it's going to be accelerating. I've already put the A there for you. Accelerating. We should probably squeeze in, it's going to be a constant. Can't spell. Constant accelerating for just 1 second between 7 and 8, and it reaches 5 meters per second. So the acceleration from C to D, change in velocity divided by time, it's just going up 1 in 1 second, so that's 1 meter per second squared. And the distance travelled from B to C, I've chosen this nice bit of the graph, a nice square. It's 2 across and it's 4 high. So it's gone 8 meters in that time. And we got one more to do. Nice easy one. Goes up once. Straight line, constant acceleration. I'll squeeze constant in there as well. For 3 seconds to reach 4. B to C, it's going to be a constant velocity, not acceleration. And it's at 4 and it stays there for 1, 2, 3 seconds. And then D, we've got a deceleration. Again, it's going to be a constant deceleration because it's a straight line. It's decelerating because the line is going back down, so our velocity is decreasing, and it's for 3 seconds and it ends up at 0. So our acceleration from A to B, we'll do our change of velocity, which is 4, and we're going to divide it by how long it took. 4 divided by 3, 1.3 requiring 1.3. Distance travel from B to C, so it's 3 seconds, 4 meters, 12. C to D is our triangle at the end, so when it's decelerating. So again, it's gone 3 seconds and 4, but this time we're halving it because it's a triangle. Our challenge question, why have I never asked the distance travelled when they are changing acceleration? That's because it's a curve. And working out the area under a curve is not fully expected of you at this level, and it takes quite a bit of time.